Sorry.
his course, Computational Tools in Active Matter.
Yeah. Okay.
Thank you, Rodrigo.
Thank you. Okay. Okay, so yes. So I'm going to continue with what we were discussing yesterday. So please do ask questions, interrupt whenever you want. And as I said, you can interrupt me in English or Spanish and in Portuguese. I'm not going to answer in Portuguese, of course, because I don't know, but I can understand the question. Yeah. And Italiano, yeah. Sí. Bravo. Okay, so yesterday I sent Pablo the slides of yesterday with some typos corrected. So you're going to receive them in some moment. And for example, there was a typo there that I put the elastic potential, I put the elastic force, but it should be the elastic potential. Yes? Okay, but things like that, but you can understand the differences. Okay? Okay, so I'm going to continue a bit with AVPs, with some measurements of AVPs, but before I like to discuss a bit on the implementation. So yesterday, we saw these efficient tricks to make the simulation fast. The code that I'm going to share you has not that implemented, but okay, because it's just to play around. It's not to do research in this case. But there's something that I didn't discuss is how to implement initial conditions. And it's a tricky part because because it can be done wrongly. And I remember in my case that it took me, I don't know, several months to figure out something that I thought it was correct, but it was wrong. And it was building me new phenomena that were not physical. Yeah? So how do you want to put n particles in a box? I'm going to discuss this in 2D. So we have this box. And let's think that is square. And we want to put n particles there. N AVPs, not any kind of particles. So the first approach can be like this. Put simply n particles at random, independently. Yes? But this is called the Poisson process. So you put one particle, another particle, and you continue up to n particles. Probably most of you have done this at some moment of your life, and you know that doesn't work. And it doesn't work because with high probability, and it's very high probability, that two particles are going to overlap strongly. And if they overlap, then the potential is going to be large. And if the potential is going to be large, then high forces are going to appear, and the system is going to blow up. That is, the displacement for this part, the velocity for this particle is going to be very large, and probably in one time step is going to do, I don't know, escape to infinite, very far. And then you have to take particles back again into the periodic boundary conditions, but nevertheless, it's a mess. You can do things to avoid that, but to smooth that out, but it's not the best solution. So the second approach is put the particles, but considering excluded volume. And this is done in several ways, but the most naive way is to put one particle. Then, for the second particle, you try here. You say, okay, is this position not overlapping anybody? Okay, I accept it. Then I put the third one, fourth one. Then I tried here. It's overlapping, so I reject that possibility. Try a new one. It's not overlapping, and you continue. Okay. It looks a very good approach. Here are the... Okay, so the first one, the problem is that they overlap. The second approach has the problem that it is slow. It is slow because for the last particles, you have to try many different positions to put the new one, and eventually you can never succeed. And you can run forever, literally forever, because actually, and even if you succeed, and I am not writing this there, but even if you succeed, the configuration that you're going to create is also very artificial. It's more like a DLA, a fractal structure, instead of a pack system. And it is, because it's sequential, for example, you can put particles like this, but by chance, the third particle was put there, and then there's no possibility to put the third one, a fourth one here. It's always going to overlap. We know that the optimal solution that the system looks is to put that particle a bit down and then put the fourth one. But this, because the system is sequential, one by one, it's not going to produce that. It's not going to correct itself. So this is not the best solution. The next attempt is this one that is very tempting. Is you have to put n particles, so you create a grid of possible positions, a regular grid. Okay? And for that, because it's a regular grid, has an x sides on these positions. And what's the value of an xy? And xy and xy are simply the what do I put? N or row? No, okay. The grid size, you have to compute, the square root of n. But normally, if you want to put 1,000 particles, the square root of n is going to be a irrational number. So you compute the next integer. So for 1,000, I don't know which is the next integer, 30-something, okay? And you create a grid, a regular grid of that size. And then you start putting the particles. 1, 2, 3, 4, 5, and imagine that you want to put, here I have 12, 14 particles. So imagine that I have n equal 14, so an x is going to be 4. So you create a grid 4 times 4, but you put your 14 particles. And then you stop because you wanted 14, you don't want 16. And then you run your simulation. Cool, they don't overlap. If you want to go to higher densities, you don't put them in a square lattice, you put them in a triangular lattice. It can be done, it's easy. But it's highly grown. And it can be very dangerous. And it took me several months to realize what was the problem. The problem here is that if you map the density, the initial density, has a gap here. Yes? So the system is inhomogeneous initially. And this inhomogeneity has to relax. And it's going to relax following the diffusion equation. Because it's homogeneous, has to homogenize. And the time it takes to homogenize is the natural wavelength of this inhomogeneity, that is the box size squared divided by the diffusion coefficient. So you have to simulate your simulation at scale L squared divided by the diffusion coefficient just to start your simulation. Because you created an inhomogeneous boundary condition. So the system is relaxing to homogeneity. And then you start your simulation. So it's a very, okay, for 14 particles, it takes nothing, yes? But as we were discussing yesterday, we want to do simulations, I don't know, million by million, and then it can take you ages for the system to be homogeneous. So there is a better solution. So as I said, it creates log wavelength inhomogeneities. And a better solution is that you create the grid, you put not 14, but 16 particles, and then you take out 2 at random. This one and this one. And now your system is very close to homogeneity. This is a fast scheme. The inhomogeneities that are created are not localized on a region, are spread around your system, and you don't create artificial inhomogeneities. Of course, any initial condition that you create is not the steady state. Because if you know the steady state, okay, come on, you don't want to do a simulation, you know the answer. Normally you don't know the answer, so you want to create, you're going to create something that you don't know exactly, but you have to be closer to what you want to get. And closer is that you have to be you have to create an homogeneous state. So this is the trick. This is okay, there are several ways of doing that. I'm going to explain another one that we use also. That you create the square grid, you put the particles at these grid positions, but you create n particles. No, not n square particles. You create more. And then you randomly sample your n particles from the list that is bigger. And those particles are more or less, and then the holes are evenly distributed and you're not creating high inhomogeneities. Okay, so this is a way. Another way to create your initial condition is to put the particles on a grid or in a grid with holes like this, then simulate the system with the potential, with WCA or whatever, but no velocity. But you put random noise, and then particles move, then your system is not going to be squared, and then you start your simulation. There are several ways, but you have to start with something that is close to homogeneity, or otherwise it's going to take you forever. So actually, I was almost tempted to publish a paper of some new slow processes in systems, because I was finding something that relaxes very slowly, and then it was simply diffusion of the initial condition.
Rodrigo, dx and dy should be always larger than sigma, the diameter of your particles? Or?
Yes, because otherwise you cannot fit that many particles on your box. If it's not the case that those gaps, dx, if those are smaller than sigma, then you have to you have to create your grid on a triangular lattice. And if in a triangular lattice you don't fit the particles, then you cannot fit the particles at all. The best you can do is triangular. So if with triangular you cannot do that, okay, you're lost. But that means that you're trying a density that is too high. Okay. So we were discussing some measurements yesterday, and I was telling you that, okay, we defined the percolation function for densities, that is, how many particles do I find at a given distance, and also we were discussing what's the relative directors of the two particles one to the other. How do they correlate? That is, if those the particles are, this is the vector that joins the two particles, I see how is this director related to that, and there are two possibilities. Either I multiply the cos with the cos or the sine with the sine. That is doing the dot product with this vector or with the other vector, the tangent one. Okay, and this is the code I'm going to show you, but it's simply you accumulate the same things as before, and then you normalize with the total measurements. And this is the result that I showed you yesterday for this system, and I said that this is the percolation function, and my colleague complained that I was showing the case of MIPS. Yeah. So it's true, it's correct. Francesco was correct. I was not doing something wrong, but doing something tricky just to show the something extreme. So let me show you the code. So this is my dirty code. This is the initial condition routine. This is the force, okay. And I'm going to put the system on a big box. So I'm putting just 30 particles on a 15, on a box of 15. I'm going to put less particles, indeed, because I wanted to do it fast. And I run the simulation. As I told you, it's a brute force code over all the particles. And here is running. Okay. You have to be patient. I put it that because otherwise I didn't know how far it was going to take. So it's just 20 particles, I said. So it's done. And I plot the configuration, and now this configuration is not clustering. Some particles are close because they are AVPs. When they meet, they are persistent, so they want to continue moving in this direction. So there are many pairs, actually. There are many pairs, and that's what we saw yesterday. So this is the percolation function. It's much noisier because my simulation was shorter and less particles, but this is the percolation. Many particles at contact, and then almost flat. And yesterday I asked you what is the shape of this tangential and parallel and perpendicular components of the correlation. So we have particles like this. This is phi. The other particle like this. This is phi. And I have the correlation parallel. And this is, sorry, N1, N2, and this is R. So this is the average. And C perp is the same thing, but with that values. So this is T. Recall that T appears twice, so you can define T in this direction or T in the opposite direction. Nothing is going to change. So you can use any of them. Okay, what do you expect after thinking after the years? So what are the shapes of those two functions? Any guess? Okay, but recall that this is a function of distance, so you say that the particles are moving in this direction. So one particle is going to point along R, and the other particle is going to point along minus R. So you get something that is negative. Yeah? Yes? Everybody agrees that for the parallel part, they're going to point like this. Okay, negative, okay, this is sigma. They don't know before sigma, that sigma is negative, and then and for the perpendicular part, I have to admit that I don't have too much intuition on that. So I'm just going to show you the answer, and we can discuss on this. This is a hidden slide, and those are the parallel and perpendicular part. No, they're not going to appear because it's hidden. And skip. The parallel part, as Pablo said, starts like this, but rapidly goes to positive values. So for this, this peak here is for all those particles that are exactly at contact, and then the particles that are not exactly at contact, they tend to move more or less parallel. And for the C perpendicular is negative. And do you know that? Why is that? So the other one is saying that they're like this, but if they're not contact, they're moving. This part is because when they meet, they have to slide on top of another. So when they're sliding, they move anti-parallel compared to that. That is, this, in this case, this is the perpendicular vector, so they move perpendicular, one moving in one direction and moving in the other direction. So here finally, we got something that we were not expecting. That's why we use simulations. We don't use simulations to get what we expected, otherwise it's cheaper to write an Aristotelian article just out of your thoughts, but you run simulations and you discover new things. And then you have to explain that. And finally, and this is not my job here, you have to think if those things that you have found have some relevance for the phenomena. Yes?
So at that distance, the typical configuration is a dimer.
Dimer, at that density.
Yes, so if the dimer does not slide, if it stays there,
Yeah?
then you should not have that, right?
Yes, but
have
dimers
cosine
is...
pi over 2 times cosine pi over 2.
Yes, but dimers are not going to stay there forever, because for that you need exactly oppositely moving particles. If they're just a bit shift off, they're going to...
And that's because you have a little bit of softness in the particles, right? If they are completely like...
No. Because they are going to stack if they're exactly in this configuration. But if when they first met, they were something like this, they're going to slide slightly because they have a small component of the velocity that is tangential, and this component allows you the particles to slide on top of the other.
If you had a rejection method, like, or an infinitely hard potential, would you
Infinite hard
still
potential.
have the same?
Yes, have the same. Yes, because they enter, you reject a bit, they enter, they reject a bit, but they have still a component of the tangential velocity. Only for head-on collisions, it's infinitely long. Okay? Yes, sorry. Sorry.
If we have soft disk, we are going to see the same thing.
Actually, those are soft disks.
Okay.
Because
Yeah,
I was running the simulation, a fast and dirty simulation with
Right,
very soft
that's
potential.
right.
But if you do it hard, you get the same.
It's similar.
Yeah.
Thank you.
Okay, so that's one thing that you can measure on simulations. Okay, so probably that's where I stopped yesterday. And now I'm going to describe other kind of fields, other kind of quantities that you can measure. So I think I've been describing percolation functions. Now I'm going to discuss spatial fields, mean square displacements, and that's it. So for the spatial fields, this is very simple, but something that has to be said at some moment of your life. Okay. So here we have, I want to run the simulation because it's fun. Okay, so here we have AVPs. There's a hard wall, so on top of all potentials between the particles, we have a potential with a wall. There is a repulsive potential, so particles cannot enter into the wall. And because they are persistent, they accumulate on the wall. So they move towards the wall, and they can escape if they change direction. But during the time it takes to change direction, new particles are going to come, and they're going to block that one. And the blocked particles is going, this particle now is pointing anywhere, but it cannot escape because it's blocked. So you create a wet film, a wetting film in this case. And the density, you like to say there's something like this. Okay, so I'm going to say this several times in this week. Never or avoid recording trajectories because it's too expensive, and anyway you have to post-process the data, so do the analysis on the fly. And do the analysis on the fly means that if you are running your simulation, you do whatever you do for the simulation, and when it's time to measure, okay, you're not going to measure at every time step. You want to measure after the transient, for example, and every 100 time steps. You say, okay, I just made another measurement, and then you run over all particles. And for the density field, you have to bin on the position. In this case, it's 1D, so you just bin on 1D. So you have a binning length, and you say the bin that I'm going to use is the position of the particle divided by this delta x. So the particle is here, but then I'm going to be in the bin 0, 1, 2, 3, 4, 5. So you bin the system, and then you accumulate by 1 the number of particles in the bin. You simply accumulate. You don't compute densities at that moment. You just accumulate. And then at the end of the simulation, or not necessarily at the end of the simulation, whenever you want to record some data, because also something that I learned when I was young, but that we have some electric cuts from now and then. So it's good to save your data from time to time. Yes. So at the end of the simulation, or at some proper moment, save your data, and your data is that. You run over all the bins, and now, just now, you compute the density. The density is the accumulated number of particles divided by the number of measurements and divided by the area of the bin. The area of the bin, because you have a 2D box, you are binning like this. So this is the area, is delta x times Ly. That's a density. This is 2D. I'm writing everything here in 2D. And that's what you record. So you don't record all the positions or wherever. It's too expensive. Okay, but here we're discussing of AVPs. So AVPs also have directors, and normally you want to record the polarization field, P. The polarization field I think that was also called P by Julia, is the average of the directors on a bin. Sorry.
I have a question about the dx of the bin.
Yeah.
Has to be longer than the particle radius, or doesn't matter?
Okay. I remember that was a long discussion on the granular community. Okay. The question is, I have the box. Do I have to do bins? Here I'm plotting a 2D bin, yes? Do I have to do binning larger than the particle or smaller than the particle or whatever? It depends on what do you understand by density. You can define densities as the densities of the centers of the particles, saying that the particles are just located on the centers. Indeed, if you understand densities as like this, that the particles are just located on the center exactly as a direct delta, then you can make your beams as thin as you want, because the particle is just exactly at the center. Yes? This is the understanding of the community of liquid matter from the 80s, let's say. But now, in granular materials, in grains or colloids, you say, okay, the matter is all inside the particle. So you want to allocate a kernel to the particle. The particle is, the density is not that, but is some kernel like this. Yes? That, for example, have a spherical shape, a Gaussian shape, whatever. And in that case, maybe you want to do beams that are thicker than your particle. Yes? Okay, that's the short and complicated answer. The simple answer is always, always do that. Always do that. I'm going to call this micro and this coarse-grained or soft, let's say. Always do that. It's simpler because you can make your grid as thin as you want. Why I say always do that? Because if you know this expression, if you measure that thing, you can always get that. Because simply it's the convolution of the kernel with the microscopic density. So if you got your microscopic density, then you can get a softer version of the density. The opposite is not true. You know, it's not easy to deconvolve. So if you made a convolution, if you already made a convolution, deconvolve to get the microscopic density is not going to be easy. So get your microscopic density and then do whatever you think is appropriate. For example, say that the mass density is allocated all inside the volume of the particles or whatever. Yeah? Everybody agrees? No, you don't agree.
Yes, I agree. Just want to understand the difference between the two cases. You mentioned the liquid community and the granular matter community. I mean, the density of material is distributed in the particle homogeneously, right?
Yeah.
So outside there is no material, and inside there is material. So it's
yes, but you can always think on the center of the particles.
Yes, if they have no size, then you consider only points.
No, even if they have size.
Okay.
You consider particles to be points. Points with a potential.
Yeah, okay, I see.
That is, in this figure, you are thinking of particles as being points, mathematical points, interacting with a potential. In this picture, you are thinking of particles as solid bodies, interacting, I don't know, with an elastic force to be impenetrable. But you can get that out of that. Okay, so we have densities. The next thing is to have polarization, that is the average of the densities, and this is done exactly the same. So you simulate over time. When it's time to measure, you run over all the particles. For each particle, you get the bin where it's located, and then you accumulate the density, summing simply 1, because you count the number of particles, and you accumulate the polarization, simply adding the directors. And then the polarization field is going to be the accumulated polarization divided by the accumulated density. That's the definition of an average. Of course, if you run this code in your computer, it's going to give you some errors. and you have to do the proper programming, because if you want to divide, if in a cell you don't have any particles, you're going to divide by 0, and okay, it is going to fail, but this is the idea. Yes, that's the way you get averages. Okay, but the polarization, as I said, is the average of the density, average of the directors, and the directors were this vector, cos phi, sin phi, in 2D. So in 2D, the polarization is the average of the cos and sine. Yes? So that's what you get. Here, when I said that I accumulate the director, actually I'm accumulating the cos and the sine of the directors. It's the same thing. Or the x and y component of the directors. Okay, but it is possible, as you're going to see in Pablo's poster on Thursday, that when you have a thick wall, like in the case we were seeing the video, particles accumulate like a thick wall, but just outside the wall, outside the film, particles move in a nematic way. Nematic in the same sense as Julia was discussing. That is, particles move parallel to the wall, up and down. Not in a vectorial way, that is, it's not essentially up or not essentially down. Half of the particles are moving up, half of the particles are moving down. And essentially, it is a selection mechanism. Particles that move on the x direction are going to be absorbed by the wall. Particles that move in the opposite direction are going to be escaping from the walls. So particles that are there are the particles that are moving parallel to the wall. There's no force that aligns the particles, but it's a selection mechanism. You select, it's a bias here. So how do you measure that? Is, as Julia said, with the Q tensor. I'm not writing exactly the same Q tensor as Julia. I'm going to discuss that in a moment. So this Q tensor is a tensor. In tensorial notation is the director times the director. That means that I'm going to compute the average of nx and x and x and y and x and y and y. So 4 components. Yes? So here is, okay, so you have all the particles and those averages are computed like this. You accumulate all the components. So you build and then you compute at the end the average. And in this example, for example, in this position, the Q tensor is going to be essentially this thing, 0, because you have no particles pointing along x, 0, 0, because you don't have particles pointing along x, and here you have a Q, because you have particles moving up, that gives you positive, but moving down, it also gives you positive because it's squared. Okay? That's the Q tensor. That's the information that you get from the Q tensor. You get organization of the system. Okay, but the nematic tensor is nx and x and x and y, whatever I said. And then you remember, nx is cos of phi, and y is sine of phi. So this is cos squared. This is cos sine, this is cos sine, and this is sine squared. Yes? But from your high school, you remember that cos squared is 1/2 of 1 plus cos of 2 phi. Yes? Cos phi sin phi is 1/2 of sine of 2 phi. This thing is the same thing, and sine squared is 1/2 of cos 2 phi minus 1. Yes? So is this object the same thing as the same thing? And you have this 1 on the, sorry. You know, another mistake. So I have to write it properly. Q no, yes, Q is to 5 plus 1 sine to 5 sine 2 phi 1 minus. Yes, the sign is wrongly there. So that's what Julia yesterday wrote. That is 1/2 plus cos sine sine 2 phi minus cos 2 phi. Yes? And this is the one that she was extracting yesterday, because she was defining Q as this matrix minus 1. This is the one. You remember? Direct delta. Okay. But it is not going to change anything, because also you remember from Julia's talk that the force that appear on the Navier-Stokes equations, we saw it today, is divergence of Q. So if you, to Q, you add a constant, nothing's happening. So you can add or not add this one, and okay, you don't care. Okay, so the nematic tensor, now when you see it like this, is nothing more than the average of the second Fourier mode, cos of 2 phi sine of 2 phi. The polarization vector is the average of the first Fourier mode. So you have the density, that is the average of 1. The polarization vector, that is the polarization of the first Fourier mode, and the nematic tensor, that is the average of the second Fourier mode. Yeah? So now if you move to 3 dimensions, in 3 dimensions it's the same thing, but you don't work with the Fourier, you work with the spherical harmonics. So the Q tensor essentially are the averages of the spherical harmonics of second order. Yes, because it's a nematic one. And now with different m's. And you remember from your course of mathematical methods or from high school when you knew the orbitals of the electron or the hydrogen atoms, that m runs from -2 to 2. So you have -2, -1, 0, 1, 2, 5 different numbers. As Julia said yesterday, that in the Q tensor, you have 5 independent quantities. It's the same thing. Yes? It's a different way of seeing it, that you can write it as a matrix, but it's a matrix that is symmetric, traceless, and so you have just 5 components, or you can think on spherical harmonics or Fourier modes that you have also the same kind of quantities. Yes? Also, yesterday, she said that in 2 dimensions, there were just 2 components, and here you see that there are just 2 components. Okay, so this is what you can get from fields. Next thing that you want to measure, fluctuations. Because, yes?
Sorry to interrupt you. So the size of this nematic stripe should be the persistence length?
The size of this nematic stripe? Not really. It's much thinner. I will have to think on why the size of that.
Maybe because of interactions, I don't know.
Yes. No, I don't know exactly. It's very thin. Okay, so density fluctuations, because those systems, in many conditions, are homogeneous. Francesco was showing yesterday, for example, in this V-shaped model, that in some phases the system was homogeneous, but it's highly fluctuating. Yes? So how do you measure fluctuations? So the system is, there's no question marks here. It's a close of the parenthesis, my mistake. So what information can you get if the system is homogeneous on average? So I was discussing just before the microscopic density. This is the microscopic density. You want to see how it fluctuates. The problem of that density is that it is completely unfit for numerical analysis. You cannot represent on a computer a Dirac delta. Yes, it's infinite or zero. So if you want to represent that, you can bin your system, but it's not going to be a proper, a very exact representation of your Dirac delta. So this is not very fit for computers, the Dirac delta. But if you Fourier transform the density, you compute the Fourier transform. That is, this is the Fourier transform, and this is my signature with a plus here and no 2 pi factors there. This is the Fourier transform. If you Fourier transform a Dirac delta, the integrals are very simple. For every delta, you replace r, but ry, ri. So you get that the Fourier transform of the density is this sum of Fourier modes. And that expression now is very adequate for computers. There's nothing infinite there, just complex numbers that you can compute quite easily. Okay, now if you compute the average of that, this is going to be 0, essentially. All modes are fluctuating, sometimes with phase 1, sometimes with phase -1, sometimes with phase I, minus I, whatever, and then you get your average, and your modes are going to average to 0. Yes? That's in a homogeneous case, because I'm considering here an homogeneous case. But then, if the average of that is 0, you can compute the variance of the modes. That's the variance of the modes. That is the average of the amplitude of the modes square. Because they are complex numbers, you have to put the absolute value. This is called the structure factor. And the structure factor is going to give you information of the amplitude of the fluctuations at different wavelengths. So if your system is fluctuating, it's not going to fluctuate equally on all wavelengths. Some wavelengths are going to be more predominant. For example, if the system is going to develop some patterns, but it's still homogeneous. For example, yesterday, for the Vicek model, we saw that there was a transition, you remember, from homogeneous, it was called homogeneous liquid, no? In your case? Oh, homogeneous. I want to put the word homogeneous, sorry. Polar liquid to stripes, moving stripes. Yes? You have these stripes that were moving like this. And then you have the cluster phase. You remember? So just before the transition, although the system is homogeneous, the stripes are there. Are there in the sense that the structure factor is going to be larger for that wavelength. Because those stripes appear, but they are unstable, so they disappear. They appear, they disappear. And also, if you look here, you will see the stripes as the amplitude of those Fourier modes. An important thing is that the K cannot be anything. Should be, I have not said that, but I think I'm going to say it tomorrow because I need to prepare that. But all simulations normally you run with periodic boundary conditions. There's particles that escape on one border, enter into another border. So the wave vectors should be commensurable with the box size. That is, they have to be, oh, no, that's a horrible mistake. I'm going to correct it immediately. Okay. So the wave vectors cannot be anything. They should be 2 pi n divided by L, where n is any integer number in a cube in 3 dimensions. Okay? So that's the structure factor. But the structure factor, there's a nice relation, and it's going to give you some insight on the system. So this is the Fourier transform density. So the structure factor, as I define it, is the amplitude, is the variance of the mode, of the amplitude of the mode. So the absolute value square is the same thing as the complex conjugate times rho. each row is this thing, is an integral. So I have 2 rows, I have to put 2 integrals, but one of them is complex conjugate, so it has a minus sign there. And there are 2 integrals of 1 integral over R1, R2, so you have row of R1, row of R2. And it's the average. Bloop, bloop. And the only average that you have to take is over densities because particles are moving all around. Yes? Those things are those direct deltas that I just discussed, but okay, don't worry. You have to compute this integral. Now, we can define the density correlation function that is, in the language of Aparna yesterday, is the connected component, is the connected part of the correlation function. That is the correlation between the 2 densities minus the average of the density times the average of the density. If you have an homogeneous system, those averages are simply the density squared, and the correlation function is also only going to depend on the relative distance of the 2 particles, of the 2 points that you're observing. So this is the relative distance, and this is that. So here you can replace this object here as G plus rho square. So the structure factor is this thing. And just to make things a bit slower, but you have to complain if you are running fast, I'm going to do this integral here. It's a 2-step integral. So you have S of k is the R1, the R2, G R1 minus R2, plus the R1. No, sorry. There's an important factor that I was missing, the most important thing. Okay, I have to do this integral. So for this integral, I do a change of variable to the relative position and the center of mass. Yes? You do it several times in your life. Yes? So this part is simply dr, rho square goes out, something like this. The first integral is simply the volume, because nothing depends on the center of mass, because the system is homogeneous. This integral here is 0 for all k's, because it's a sine function, a cosine function, so it goes 0, except if k equals 0. If k equals 0, this is 1, and you have to integrate that, and you're going to get then another volume, but now only if k equals 0. So this is what is said there. B square, rho square, delta. Here you do the same change of variable. You integrate over the center of mass, and you integrate over the relative coordinate. This integral is going to give you a volume, and the other thing is what is written there. So you get, for the first integral, b dr, this exponential, because you change the variable, g of the relative distance, plus this term. So what we discover is that the structure factor that is very easy to compute, because you just have to compute the Fourier modes. The Fourier modes, as I said, they are computed like this. And then you compute the variance of that. A variance is simply you average the square of that. the structure factor is nothing more than the Fourier transform of the pair correlation function of the density. So it's going to tell you how the system is correlated along distances. So it's the same information. What is the amplitude of the different wavelengths, of the fluctuations of the different wavelengths, is the same information as how the density fluctuations are correlated. That is, if a bump is created here, how is the density nearby? Is also high, is opposite, etc. Yeah? And, okay, so here I'm saying the same. And for example, typical things that you get is a structure factor like this. For example, a Lorentzian. This is the typical fit that you do for that. So it's an amplitude here, and it decays at some distance k0. It depends on the wave vector. And now, because of the Fourier theorem, the Fourier theorem tells you that if S is the Fourier transform of G, G is the Fourier transform of S. Yes? And you know the Fourier transform of the Lorentzian. You learn that in, I don't know. Normally, you learn that on quantum mechanics too, when you compute the scattering cross-section of the Colombian potential, of the Yukawa potential, things like that. You learn in several contexts. But the Fourier transform of the Lorentzian is this thing, exponential of minus k0 r, and I put things like that because that depends on the dimensionality. Yes? In 1D, it's simply e to the minus k0 r. In 3D, is that. Yes? And in 2D, is the Bessel function k0. Yeah? The incomplete, I don't know the names of the Bessel function, but it's the Bessel function that is not oscillating, the one that is exponential. Yes? Okay. But what is relevant is that the correlations decay at that distance. So when I say if a bump is created, densities nearby have the same increase of density up to a range k0, 2 pi over k0, to give you a length. Another case that you can get is that the structure factor is something like this. A bump, but it's not centered on 0, it's centered in another k0. This is the case of that, of the Bishop case. In the Bishop case, if you compute the structure factor, you're going to get something like this, and if that is a direct delta, but I put an epsilon, it's a wide delta. Okay, something like looks like a delta. A wide delta centered on k0. And if you Fourier transform that, it's something that is periodic, almost. Almost because it's only periodic if it's a direct delta, a truly delta, but if it's wide, you get something that is almost periodic. Meaning that the things have a period. To be more concrete, if you have that the structure factor is something like this, the correlation function is going to be something like this. Periodic, but damped. That is, if you're very far, you are not correlated. But if you are close, you see maximum, minimum, maximum, minimum, maximum, at any snapshot, like here. So it's much simpler to compute structure factors and then Fourier transform to get the density. Okay, I'm not going to explain how you measure that because it's direct. It's the same thing as before. Okay, so now we enter into the mysterious world of mean square displacement that I think is important probably to see it 3 times in this course. I think Aparna is going to discuss that tomorrow or today. I don't know. I don't know when today she's going to talk. And maybe from the Vichek model also you're going to discuss the mean square displacement or no? Okay, the structure factor. Ah, okay, that's cool. No, okay, so you're going to see just twice the mean square displacement in those curves. So it's good because it's an important tool. So if you don't have a net flow, because if particles are swarming in one preferred direction, you don't need to compute the mean square displacement because there's a mean displacement. Mean, not mean square, mean displacement. They move from here to there. Okay, that's the easy case. But now, if particles are not moving in a preferred direction, there's no net flow, but anyway, you want to compute how they move. So if the average is 0, the next thing that you do is you compute the variance. Yes? And the variance is that you define the mean square displacement at a time gap t as the distance traveled from t, an initial time, to that initial time plus t, so a distance t in time. So you compute the distance traveled by the particle, and you square that distance. Here you should be, I don't know, the modulus of the vector. Okay, so you compute how much distance a particle traveled during this is delta r, during a time. And you average over all possible initial times and all possible particles. Okay, so the first case, the very simple case, is imagine particles that are infinitely persistent. That is, they move forever in the same direction with the same speed. Okay, this is not active Brownian particles, it's just whatever, particles that just move. But in this case, the position at a time is simply the initial position plus the velocity times t. That's the kinematics, high school kinematics. Then the difference is simply BIT, and the mean square displacement, you have to average BIT squared is simply the average of BI squared, T squared. So if you see that your mean square displacement is quadratic on time, this is quadratic on time, it's telling you that the particles are ballistic. They are moving persistently in the same direction. And you get two things if you get this result. You are getting that particles are essentially persistent, and also you get the average of the velocities, the mean square velocity. Yeah? Okay, there's other ways to get the mean square velocity, but this is a way to get your mean square velocity. Also, you know, and this is what we're going to discuss, that if particles are diffusive, instead of moving the mean square displacement growing quadratically on time, it grows linearly on time. And grows linearly on time with this law. There is 2 times the diffusion coefficient, the dimensionality, and t. 2d dt. Yeah, that was Einstein, well, in his work of Brownian motion, that says that. This is the signature of diffusion. If it's growing linearly on time, it's the signature of diffusion. I'm going to demonstrate that relation in a moment. Okay, so for AVPs, we expect neither this, neither this. For AVPs, we expect both. Because AVPs, if you look at trajectory and you look at short times, they are persistent. They're moving at straight lines. So at short times, you expect AVPs to be ballistic and growing parabolically, the mean square displacement. But then at long times, you see, well, this is a drawing. You don't see. You have to trust me because it is a drawing. It's not a simulation. But you see that after a while, particles lose memory and they start moving in another direction, and it's a random walk at long times. So at long times, you expect that the mean square displacement grows linearly on time. Normally, this is not what you see on papers. On papers, typically, people plot the log of the MSD times the log of t, because in this case, you see clearly that the quadratic part goes like a slope 2, and the linear part goes like a slope 1. Yes? So this is the signature. This is what you expect from AVPs. For that, you don't need to do simulations, because we know it from, I don't know, from just thinking of the problem. And I think that Aparna today or tomorrow, she's going to demonstrate actually that this is the mean square displacement for AVPs. Yes? Ah, sorry, yes, the microphone.
Just to complement, I guess that initially if you have thermal fluctuations, you could have an initial diffusive, then ballistic, then diffusive.
Ah, yes, okay. Yes, okay, yes, I'm going to come back to that before changing the slides. Okay, so if you get that, no surprise, this is AVPs. This is what you put on your system, that they are ballistic, and then they are changing direction. There is a crossover time that, when you change regimes, that is actually when you move to diffusive, and this is the persistent times. Yes? Because it's the time before the director changes. Now, if you increase the density, the diffusion coefficient changes, but also the crossover time changes. And I want you to guess okay. The diffusion coefficient is going to be that. Aparna is going to show you that in the afternoon. At zero density, that is for independent particles. And the crossover time is going to be 1 over dr, is the memory time, is the time it takes particles to change director. Okay, so this is my initial information. What happens with the diffusion coefficient and the crossover time when you increase density? What do you expect? Yes, but what happens with the diffusion coefficient and the T naught?
Decrease?
When you have higher density, particles cannot move freely because they're colliding with others. So actually, the diffusion coefficient is going, at the end, I don't know exactly here, but at the end is going to decrease.
Like the square root of the velocity?
No, I don't know. I say eventually it's going to reach 0. 0 because particles are going to be jammed. And they don't move anymore. The diffusion coefficient, although they want to move, they don't move anymore. And what happens with the crossover time? The crossover time is when particles stop moving ballistically.
Decreases too?
It decreases too, is because even though the particle was pointing this direction and the director is not changing, if it encounters others, that particle is going to be blocked, it's not going to move, despite it's pointing in the same direction. So it's true, it's going to decorrelate the director and it's going to escape. But it was not moving, so the displacement is not like that. If the system is much denser, it's going to do something like this, stop here. So the distance travel was much smaller, and the system stopped being ballistic and start being diffusive before. Okay? That's your homework for today. Get those curves. Yeah? Okay. Yeah? Okay. Numerically, of course. Yes, no, analytical. Okay. You get a very nice paper if you compute that analytically. Yeah.
And including the MIPS regime?
In the MIPS regime, yes, yes, it depends. It can become negative.
I mean, the effective diffusivity as a function of persistence time increases first, and then it decreases because of clusters,
Yeah.
right?
Yeah. Yeah, but that changes the density, not the persistence time. Yeah. Yeah. Maybe that can be, but it can be negative, but negative if you do it, if you start with an homogeneous state, because the homogeneous state is unstable for the instability. Yes, sorry. Yes.
In this type of model, is there a possibility to have the caging regime in the middle of the boat, or no?
Caging, I just wanted to talk about caging now, so little spoiler, but it's okay. But before that, let me discuss on something, comment on something that Ignacio was asking, that the AVP model that I'm putting is that. Okay. This is the AVP model for me. Yes? Particles move with some director, particle forces, and the director is changing randomly. There's another version of the AVP that says that as particles are microscopic, micron-sized particles, Brownian, colloidal, active colloidal particles, or bacteria, or whatever, they're subject to Brownian motion. So there's a second version that puts something like this, that they're subject also to Brownian noise. This is translational Brownian noise. If this is the case, the mean square displacement is like this. Log MSD, log of T, the MSD is like this. At very short times, you see diffusive motion. At very short times, you see this diffusive motion because of noise. This is Brownian noise. Then particles move. This is self-propulsion. And then you have active diffusivity. Yes? This is the mean square displacement if you add this term there. Yeah? Historically, there are many papers that put that and many papers that they don't put that. Yeah? At the beginning, I think that almost everybody put that because they wanted to be more realistic and say particles are microscopic, so okay, you have to put Brownian motion. Then people realize that it's true that this factor is there, but it's not really changing anything on the phenomenon. So the phenomenology for the active matter systems is almost the same if you add this or you don't add this, almost. I know that Pablo is going to complain, but I'm not letting him to talk, so it's almost the same. Yeah? You have the mic, but you don't have the power. Okay, so what we're saying is that actually we're going to observe the system from here. A long times longer than this. It's true that noise can play some role, and I'm going to discuss that tomorrow. Yeah? Okay. Yeah? Okay, so this is what you get for AVPs. Actually, nothing very new, but you can get new things. For example, if you go to very dense systems, you can get that the MSD looks like this. You don't see very much what's going on. But if you take the log looks like this. So clearly a ballistic regime, clearly a diffusive regime, and something in between. That I put a 0, meaning that it's not growing on time. Normally it grows with a very slow slope that normally is not a power law, so that you don't put a slope. But it grows slowly, that's what's drawn here. But it's not ballistic, it's not diffusive. It's something in between. And this is interesting, because now you start seeing things that you didn't put explicitly on your model. So you're getting new phenomena. That's why you're using computer and Manif to do the simulations. Yeah? So it's a signature of new phenomena, and as you said, in this case, it's caging. Caging means that the system is so crowded that the particle move ballistically, but then remember that the MSD is the average from an initial condition to a farthest time step. So it's from any initial condition. So whatever they are, normally, if you look for a short time, the particle is going to move. Yeah? So at short times, you are going to see ballistic motion. But then they block. And they stop moving. And then, but that depends a lot on the model. On AVPs, that's really hard to see because you get instabilities and other kind of stuff. But you can get caging, that the particles are, and then eventually the cage opens. Why the cage opens? Because those particles are also active. So they change direction, they let the particle escape, and the particle goes out. And then, but because it went out in an uncorrelated direction compared to the initial one, it's going to be a diffusive motion. It's not that they stop like this, and then when the cage open, continue moving in the same direction. In that case, it will be continue being ballistic. Normally, it changes direction in between, so you get something that is diffusive. So the MSD is going to tell you a lot of what's going on in the system. Okay. And with this, I'm going to finish. I think I have, this 10 minutes, is enough to do the calculation. I'm going to do now an analytic calculation for you. And then tomorrow, we're going to continue with simulations. But it's important to see, to understand the theory before when you're doing some simulations. So sometimes you get something like this, that the log of the MSD, the function of time, grows first ballistic, and then with an exponent that is not 1, smaller than 1, for example. So it's called, if it's smaller than 1, it's called subdiffusive. If it's larger than 1, but not 2, it's called superdiffusive. But you get something that is different from 1, and the question is, how do you interpret that? What is going on out? What is happening here in this system? So I don't know if you have some idea. Sorry.
Yeah, I was wondering if when you have chiral particles, the MSD looks like a fluctuation, like like an oscillation, right?
Yeah.
In that case, would you measure all like the average of the oscillations in order to say something about the diffusive motion, or?
Yes, okay, so Francisca is asking me about particles that are chiral. I think that tomorrow we're going to see experiments of chiral particles with X-Bucks. Yes. So particles that have a tendency to rotate on top of other things. So the trajectory of a particle is essentially that. Doing circles, but circles are not perfect because you have noise, and eventually it diffuses. So chiral particles, if I have some chirality, you get something like this, and the MSD is going to do something like this. And then you get a long time diffusivity.
Yeah.
Yes. So you fit that to a straight line, and you get the diffusion coefficient at long times.
Okay.
Yeah. Yeah.
When you have the case before the previous slide, when you have the cage, you have a characteristic time for the cage to open, or it occurs at a random?
Both. Yeah. It's random, but with the characteristic time. Typically, it's a Poisson process. That is, it's an exponential distribution of opening times, but with a characteristic time. Yeah? And this is actually an important subject of research, is to determine those characteristic times for the opening of cages. Not for active matter, but in the soft matter community, a lot of money is put on opening cages or closing cages. Yes? If you want to produce a foam, a stable foam, you want that the bubbles do not diffuse. So you want cages to be highly stable. Yeah? If you want, I don't know, in a reactor to have some chemical reaction, you want cages to open for the components to mix. Yeah? If polymers, this is the famous model of the gen of polymer reptation, how polymers flow, is a caging process. As his very famous result is that he predicted how the cage time scale with the polymer size. Like length to some exponent 4.3, whatever, I don't know. He computed that. Yeah. Yes, so you want to know that characteristic time. Yeah.
Okay, thank you.
And also in active matter, right? There is
yes.
caging of tissue cells in jamming situations.
Yes, of course.
And you are worried about cancer cells that should not cage out.
That's true. Yes, or in healing, you want cells to migrate and not to be caged. Yeah.
You said about Poisson process. I think it might exist an analogy with run and tumble. It's a tumble, no? It's always, but a tumble that spends more time, no?
I didn't understand
the caging is like the particle will in the dense suspension will like it's similar to a tumble in a
yes. Okay, typically that is once you understand the caging time, that is an exponentially distributed caging time, it's an caging characteristic caging time, and you have that the escape is exponentially distributed. Now people, instead of modeling the proteins that vibrate, and then you have to simulate with picosecond time step, because that's the typical time step for molecular simulation of polymers. And then it moves in a scale of 1 second, so very slow. Instead of doing that simulation that is going to take you for ages, what they simulate is the blob that is doing jumps like this, exponentially distributed on time and sometimes with a distribution of sizes, like random tumble.
Oh, yes.
Yeah,
Thanks.
that's how people model sometimes those escapes of cages on a coarse-grained time scale. Yes.
I also have a question about the caging process. When you have like AVP in a confined space, your MSD will look also like reaching a plateau. So it's like this plateau is not related with the cage or this or your the size of your
Yes.
confinement or.
Yes. Okay. Now, I'm not going to get to the. Okay, it doesn't matter. It's better to have questions. So, if you have your AVPs on a confined space, yes, I invite you to read the paper that we're going to send soon with the student. So he's studying bacteria inside the droplet. So they diffuse, they have ballistic motion, they diffuse, but they're inside the droplet, so they cannot escape. So the mean square displacement, the displacement, sorry, this thing is bounded by the diameter. It cannot get larger. You can never move to larger distances than that. So the mean square displacement is going to saturate to a value. So normally you get ballistic, diffusive trapping. It's not called caging because caging is when you have cages that can open and particularly eventually can diffuse again. This is confinement. And in this case, you get that the system cannot diffuse. Yeah. Okay, I don't know if they have more questions.
Anyone else?
Okay, so we're not going to get into, not today. Tomorrow, we're going to see what's going on here. Yes? And in the process of understanding that, I'm going to show you why you get that. Why this is the standard result. Yes? And what you have to do to get something non-standard, like an exponent different from 1. Okay, but for that I need 15 minutes that I don't have it today. Okay?
Okay.
More
Thanks a lot,
questions?
Rodrigo.
Okay, thank you.
So I'm assuming no more questions.
It's a very technical question. There is a straightforward algorithm here. There is a straightforward algorithm to find these inflection points between regimes.
Oh, you mean to get this point?
Yes, all between cage,
Yeah.
transition, all the inflection points. There is
I don't think there's a straightforward algorithm. You can do two things. You have good data. That is, okay, normally it's not the case, but if you have good data, then you try to fit a straight line here in log-log space, fit another line and another straight line, and you get the interception. Better is to do what Aparna is going to explain you this afternoon, is that there's an analytic expression for that, and fit the entire analytic expression for that. And that is going to give you the speed, the diffusion coefficient, and the crossover time.
But this analytic expression just works for the ballistic to diffusive transition.
The ballistic to diffusive. But there are other expressions for ballistic to caging, etc.
Okay,
Yeah.
thanks.
So what exactly do you mean that the translation on Brownian noise doesn't change in the system? What exactly that you mean?
Okay, that many of the phenomena that has been discovered in active systems persist being there without this term. You don't need this term to explain many things of active matter. So many.
If it is small enough, which in practice it is.
Is it small enough? Yes.
In practice, activity is always dominating
Yes.
thermal agitation.
So I said here that you have an effective diffusion coefficient. That is that value. This value is much, much larger than the thermal diffusivity. But there are some cases that this is going to play some role. But for most of the, that is, if you want to be quantitative, normally you have to include that, quantitative, because otherwise you don't fit exactly the numbers. But if you want to understand what's going on there, it's better to do it without that because of several things. But the most important for me is that you have one parameter less.
How small is this D compared to V naught?
D1, this one?
Yes.
Okay, they're not comparable directly because this diffusion coefficient is a diffusion coefficient, has units of length squared divided by time. The rotational diffusion coefficient has units of 1 over time only. So you have to compare with the thermal one. You have to compare with this other one, B squared divided by dr. And this is L squared divided by T. So this is the effective active diffusivity. And this, now you have to compare those two, and the number of these is much larger than this. Okay, but you see that here you have 1 over the rotational diffusivity. Because if the rotational diffusivity is small, particles do something like this. So you have a huge diffusion coefficient. They explore the system a lot. If dr is small, they're changing direction all the time, so it's diffusing less. Yes? It depends on your guy understudy. There are some bacteria that are really crazy on changing the direction, so at the end they're not very different from, actually, yesterday I told you that there's some cases where the people mutate the bacteria to avoid them tumbling, so they reduce the air. But there's another mutation that they make them tumble all the time.
Okay.
They do. And for those, the air is very large, and they are effectively with a diffusion coefficient that is very close to D.
Okay.
Yes?
Thank you.
Yes, Viviana? No? No, you were not paying attention, but I was talking about you. Yes. Okay.
Apparently, for E. coli in water is 10 to the 4 times larger.
Yeah.
The effective active one compared to the thermal one.
Yes, so you can't neglect that one.
Anyone
I
else?
was talking about those E. coli that are tumbling all the time. Yeah, yeah.
Anyone else? So let's thank Rodrigo again.
Okay, thank you.